Hi everybody, it's Miss Austin. I'm going to be doing the lesson 16 practice problems. Number 1, for each figure, identify any angles of rotation that create symmetry. So, got this first one right here, and if I choose right, and for me it helps to draw this in to identify the angles, right? And I'll use this as my starting point. So if I rotate that until it goes to the side, that's 90 degrees. Nah, it's not until I go down here. Now that's 180. You can see the shape is laying on top of itself. Now, if we ignore the colors, it does have symmetry. This, right? But if we were doing colors, it wouldn't, right? So right now, the outline matches the outline after 180-degree rotation. If I wanted colors, though, let me go back and, this is black. And that's black. So when I rotate this 180, the black part's on the white part, so technically it's not the same. So if we're ignoring the colors, a 180 degree works. Ignoring colors, 180 degrees. And if you want to show yourself, right, it'd be all the way there. And you could go the other way, right? 180, you can go clockwise or counterclockwise. All right, let's look at this flag here. I'll mark that as my starting. I'm going to watch this as I travel around. So I'm going to turn it 90. No. 180. My paper slid. 180. It's back on top of itself. One more time. There's 90. There's 180. So this one also has 180 degrees through the center. And you could go clockwise or counterclockwise. All right. Now this one, let's see what I got. There we go. So I've got now I'm going to turn it 90 degrees. Not quite, right? But just a little bit more and it would. And maybe how would we figure out what angle that is? Well, it seems like this is a repeated pattern, right? Imagine if I inscribed this maybe in a circle. It's kind of like our triangle problem the other day. Right? If all the way around the circle is 360, then how far was it from here to here? 120. So it's 120 degrees that gets me, oh, here we go. There's 90 plus just a little bit more, 30, and I'm on it. So 120 degrees through the center. All right, number 2. A triangle has rotation symmetry that can take any of its vertices to any of its other vertices. Select all conclusions that we can reach. Well, if something has symmetry, then it means a rigid transformation, right? Reflection, or this says rotational. So rotation could map it onto itself, which is a rigid transformation. So A, all sides have to have the same length. All the angles have to have the same measure. And then it says all rotations take 1/2 to the other. Is that necessarily true? Let's just sketch a picture. If I have a triangle, an equilateral, right? So all the sides are the same because it says a triangle has rotation symmetry that can take any of its vertices to another. We know if we rotate this 120 each time we can. Now, will all rotations take 1/2 of the triangle to the other? No, only specific ones. If I trace this and I did a 90-degree rotation, right? That doesn't work. Okay, so the fact that it says all rotations, no, there's only specific rotations that would take one half of the triangle onto the next, onto the other. Number 3, select all angles of rotation that produce symmetry for this flower. So I copied this, and then what I did is I want to stare at this starting one, this petal right here, and I'm showing myself where I'm starting. So here I go. I'm going to try 45 would go halfway. So let's just go like halfway. There's 45. Is that laying on? No. A quarter of a turn. Yep. 90 degrees. See how this arrow started up here? Now it's over here. That worked. And then you could do 135. That doesn't work. But 180 works. And then hopefully you get the idea here. You got to turn it a whole nother quarter turn, which is 270. And then finally all the way around. So every 90 degrees, it has symmetry. 90, 180, 270, and then back to where we started. 90, 180, 270. All right, number 4, identify any lines of symmetry this figure has. I mean, you don't have to use tracing paper, but if it helps. Boy, there's a lot of stuff. So lines of symmetry, not rotation here, so reflection. So let's start. Can I reflect this across this vertical line going down the center? I'm just going to flip the paper. And it lays right on top of itself. Yep. Okay. What about going and going, which one did I just do? Oh, upside down. What if I flip it this way? I'm just going to, maybe that's the one I did last time. Let's do the upside down one. Okay, this, I'm going to take it and flip it across this way. So this has lines of symmetry. This one. And this one. Number 5, a triangle has a line of symmetry. Select all conclusions that must be true. So this one's a little tricky because you might think of you might picture an equilateral, right? It's got a line of symmetry right there. But then what if it's an isosceles? Just an isosceles. Maybe not all 3 sides are true. Or all 3 sides are the same. But it does have a line of symmetry, so we know it can't be something like this, like some weird one, because that doesn't have a line of symmetry, so it couldn't be that. So if you get caught thinking only about the equilateral, you might say this is true and this is true, right? It has to have some sides the same length, but we're not sure if all 3 are the same or maybe only 2. So it says must be true. So that leads me to believe it's an isosceles. That's all I can conclude for sure. And so that means these 2 sides are the same and these 2 angles are the same. If they gave me more information, then I could say maybe all the sides and all the angles. But all I know for sure is if it has a line of symmetry, I know those have to be the same and those have to be the same. I don't know enough about that. So 2 sides and 2 angles. All right, number 6. Here are 4 triangles that have been transformed by a different transformation, which is not a rigid. So rigid transformation is one that preserves distances and angles, lengths and angles. The size and shape does not change. So hopefully you can see with your eyeballs. The only one where the pre-image and the image are different is letter A. This, right, this blue one, ABC, somehow got transformed into that. That's the size and of the triangle have been changed. This one is not rigid. This one, same shape, same size, same size, same size. All right, last one. Match each directed line segment with the translation from polygon P to polygon Q by that directed line segment. So these are the line segments which tell you how it's been translated or slid. It's a slide. So kind of look for, like I'm looking at this first one. That says it started here and then it got moved up to the left. The only one where P is down below and then Q is up to the left is this one right here. And I mean, you could trace this segment if you want, right? And line it up. Is that it? P, yep. So 4 is for A. Translation 4 is for A. Now look at this one. This one is going down and to the left. P, down, and it's one of these two. Let's trace it and see. Maybe we can tell which one's bigger. Looks like it's number 2. Look at that one. Number 3 doesn't work. When I line that up with Q's over here, this one lines up. So translation 2 is this one. Translation 2 is B. Okay, now let's just, this one is also down and to the left, which we just tried this one. Let's see if that lines up. Yep. P to Q. So 3 is C. And then, I mean, you could quickly just put D for number 1, but let's make sure it works. Let's copy that directed line segment. P to Q. Yep. P to Q. So translation B. All right, guys, I hope that helped. I'll see you soon.